Our next speaker is Khoa, and he's going to be doing a tutorial on calculating the electron proton scattering rates and including transport properties such as mobility. And just as a reminder for all of these tutorials today, we just expect you to pay attention and understand what's going on. We don't expect you to follow along and actually do the tutorials. That'll be saved for the hands-on sessions tomorrow.
Let me share my screen here. All right. Should I start? Yeah. It's good to okay. Everyone, my name is Khoa. So next couple minutes, I will walk you through tutorial number 3, which you can just demonstrate how you obtain the Boltzmann-transport equation result from the EPR file that you just obtained from the previous tutorial. And also, this tutorial will demonstrate what Drew just tell you in the lecture, like how we set up the energy windows, how we choose the K points, etc. So in this tutorial, we will work with gallium arsenide. So a few words on gallium arsenide. Gallium arsenide is a polar semiconductor with a direct gap of 1.42 eV at the gamma values, which is here. So the challenge with this material is it has a strong long-range coupling between the electron and the LO phonons, which makes it quite difficult for converging our transport calculations. Additionally, in gallium arsenide, the electron to phonon scattering processes is also an important factor. We will not address it explicitly, but we shall see some of the effect in this tutorial. So right here, what I have is the electronic bands of gallium arsenide. I obtained that using Perturbo bands Khoa mode, as Yao demonstrated in the previous tutorial. I in the GitHub I have that calculation with the result, so you can do that by yourself. So I'm not walking you through that again. Below here is the zoom in energy windows. So you can see here we have the L, gamma, and X value of gallium arsenide, and the yellow part is the energy window that we use for our transport calculations. So in our calculation, we only include just a small region near the conduction band minimum. So we know that gallium arsenide will have 8 valence electrons. So the first 4 band 1, 2, 3, 4 will be filled, and the 5th band is our first conduction band. So we just want to include just a small part near the gamma point here. So that's why I set it this way. Okay, so for more information about this material and I'll work on it, I will refer you to these 2 papers. One is on the polar phonon scattering, and another one is on electron to phonon scattering here. All right, so next here, we will, before we doing transport, we want to set our energy window. So here I show you the general Perturbo workflow, which we will focus on the transport Khoa mode. Let's have a look at the interactive workflow here. This is on our main website. So if you click on the trans Khoa mode, we'll see all the required file and the output file. So we'll see before we're doing transport, we have to do all the DFT, DFPT, 1-year key to PERT. And one step is required before trans is set up, where we choose the energy window. The dash arrow means it's optional, but it will speed up your calculations. And you will see. So for example, if I click on touch F5 files, you'll see that this is required and this will be often from setup, so you will know what to do for each calculation mode. Okay, so back to our tutorial. So now I can show you how to do how we choose our energy windows to help speed up the calculation. All right, so let me to the terminal, Docker run. So I start my Docker. So it took a while to boot up. But I will go to my work folder. So so this is my Gallium arsenide folder. And as you see, I already did PW, PHP, 1 year here. Then I obtained my Q2 PERT from Q2 PERT, the EPR file. So yeah, I already show you how to obtain this. So so now our main interest will be in Perturbo folder. So so in this one, I will show you how you set up, how you compute the imaginary part of the self-energy, and then we do transport with RTA, resolution time approximation, or ITA, with and without magnetic field. All right, so first we do setup. Okay, so so in the setup, first first thing you want to do is first screen the input. So let's look at that. All right, so this is what we have. The input file for of Perturbo in this tutorial is quite simple and quite repetitive. So I just go through the parameters slowly for once. So first we set a prefix. It can be anything. Usually I set it at the name of the material, gallium arsenide. It can be anything, but you have to be consistent throughout your calculation. We set the count mode to be set up. So we set up the energy windows. We specify our grid or the K grid for calculation. So in this case, I use 160 cube for the K grid. So here you see I specify the energy window. So we know the conduction band minimum is like around 6.065. So we want to take like 400 MeV below and 200 MeV above that. So this is the only region that's matter for transport. And we will only use one band, which is band number 5, the first conduction band for calculations. Okay, so we have to also specify the F-temper parameters, which is specify the name of our temperature configurations. So that will be a separate file. So let's have a look at that. I already prepared that file. So I will just copy that from reference. Yeah, and have a look at that. Temper. All right, so we see in this file, there's 5 lines. So the first line is you only need to specify the number of configuration that you want to compute. This one is a kind of legacy features. You can have TLF here. I'll explain it in a bit. So in the next 4 lines, the first columns will be our temperature, 250, 300, etc. The second column is the chemical potential, and the last one is the carrier concentration. So Perturbo will only compute, we will only read either the second or the third columns, depending on, used to depend on how you set TLF here. So if is true, mean it will read the third column, the carrier concentration, and compute the chemical potential correspondingly. And if you set F, it will be vice versa. So the current version, we don't use that TLF because it's caused some confusion for user. So we have a separate input parameter here. So again, if you set it to true, it will find the E Fermi by reading the third column, which is carrier concentration, and false will be different, the vice versa case. Okay, so I think yes, Docker is ready. So let's just go to my work folder, Perturbo setup. So now I want to launch my job on 4 threads. So I will set export np threads equal 4. And then I can run Perturbo by calling the executable, passing the input, in, and then we will pass the output to pert.out and check it. So I use the T function. So So we run it. Never mind. I forgot to link the HDF5 files. So that's usually the first step that you want to do. It's super. Okay, now we see it. We run again. Okay, it's running now. Okay, so my calculation is done. So first, let's look at what we have here. So we have our output files that we already see in the other tab. So here it will tell you that in our specified energy windows, we have 941 K points. We made up 4224 tetrahedra for our tetrahedron integration scheme. After apply the symmetry of the lattice, we'll reduce 900 K point to only 69 K points, which is nice. Okay, so so here we see that there's some output file, there's some text file. You can actually just read that, doing some quick GNU plot with it, but this is deprecated, and we think the better way to read the output is from the YAML file. It's a readable file, and it can be processed really nicely using Perturbo-code. So just a few words on the output I have listed here. So the temper file, as we know, either column 2 or column 3 will be modified. So there's a doping output, which is the chemical potential and carrier concentration. BOS means density of state. So all of those, everything here in you can find it in the YAML file. So you can look at this. So this is much more detail in this file. So I will quickly show you what we have here. This is the output. We have the density of state, the carrier density, all the configuration you specify in the gallium arsenide temper file, some timing. So one important file here I want to show out is the tet.kpt. So these 69 point is just computed from our calculation, which is the number you see in the per.output file. So at this point, we are ready to do transport, as we see in the interactive workflows. But I also want to do the compute the imaginary part of the self-energy, because like it will speed up the calculation, and you can also learn some useful information from looking at this electron phonon self-energy of the system. So let's go to that folder. So you see in this folder, beside the input file, I've linked the EPR file, the TET file. These are linked from the setup folder. Also, the temper file has been modified from the setup folder. So now let's look at the per input. So you see here, prefix count mode is setting to in sigma, mean the imaginary part of the self-energy. We do the phonon frequency cutoff to be 2 MeV. We don't want to make that too small, too close to 0, because that will cause some issue. Delta smear is means the smearing of the Gaussian function that Drew mentioned that we use to approximate the delta function, since we are doing the finite grid. Here we have to specify the same band that we use in the setup step. We specify the tet.kbt file name, again, ftemper and find E Fermi. The last three parameters are the number of Q points that you're going to sample. Here I'm going to use 220,000 points. We do the sampling, important sampling using Cauchy function for better conversion in this polar material. The Cauchy function width will be set to 0.035 EV. Okay, so that's everything we need to run the EM sigma. And again, I will run per, and this will usually take a while, so I'm just gonna demonstrate how the calculation goes and kill the calculation, and I will just show you the output I got from previous run. So first you see that it's just some information of our input file. And now you're seeing the code is computing in Sigma. As the calculation run, it will print out the progress of the calculation, so you can estimate, so you can know how long the calculation can take. So let's give it a few seconds. It will print out some like progress of in Sigma calculation. So you see here, our calculation has finished 5%. So I actually gonna stop the job and just show you the output file. Here. So after you run the calculation, you'll see again some deprecated text file. In Sigma is what we just computed. In Sigma mode is the same thing, but it will be full known result. So the main file we want to use here is the YAML file called Gallium arsenide in Sigma. Here I'll show you how I actually process that. So this is my Python script using Perturbo-code post processor package. So first we can simply generate the object Gallium arsenide in Sigma by calling in Sigma from YAML and name the file here. Here we have a nice functions called params update. So it will automatically set up all the parameter that we think are nice for a pre-plot, which is very convenient as you see. Okay, so so here we want to retrieve. So there's some index here. This is the bands attribute. So we want the first band. We only have one band anyway. Here we have. We also want to retrieve. Okay. In Sigma 11 means the first temperature configuration and the first band, and that's will be it for. It's just simple as that for retrieving the information from the YAML file. So I'm gonna actually run that Python script, and it should show here. This is our okay. This is our in Sigma, in Sigma that we just compute. And we see that as we increase the energy, this the scattering rate increase accordingly. I also want to mention that the parameters I use for the tutorials is already downscale for faster calculation. So it might not match exactly with the experimental, but with a better machine, you can convert this better and have a better result. Okay, so so that's it for the prerequisite transport. We can go right into transport. So first I will do without magnetic field. Again, here we see that I have linked all the file necessary, the TED.h5 file from setup, EPR file, the temper file, and the Sigma I just got from the previous step. So the Sigma here is actually optional. If you don't have it, the code will just compute the scattering rates on the fly. So let's look at the input. Again, these are generally the same parameters, but you have to keep it consistent. Here, there's a both end step. It doesn't matter because we don't do any iteration in RTA non-magnetic calculation. So I will come back to both end step in the next example. So now we are ready to go to trans RTA electrons. And by the way, by default, Perturbo will compute the transport for electrons, but there's an extra parameter that you can set that to holes if you're interested in holes properties. So I can again run Perturbo the same way. And you see it's gonna pretty fast. Since the relaxation time can be computed directly from the EM sigma. So that's only take us not even 3 seconds for the RTA transport. So now we look at the result. So a few things about, again, we have some text file that I'm not gonna look at. So the conf file here, you can find the conductivity and mobility tensor. TDF is a transport distribution function that Drew mentioned. Trans coefficient, you can find the transport coefficient and thermal transport as Seebeck coefficient. So now we have YAML file, and again I also made a Python script for retrieving information from YAML file. We create an object. We retrieve the temperature information here. So we have the attribute temper value, and also we retrieve the what we have here is the mobilities. So here we interested in the XX components. So you see right here, there's 2 index, 0, 0 is corresponding to XX, and as you might have guessed, if we want to if you are interested in the XY component or XZ, you can set this to 0, 1 or 0, 2 accordingly. So the rest is just specify the plot title, stuff like that. So we run this Python script. So here's the mobility versus temperature of gallium arsenide. So as we expected physically, as we increase the temperature, the mobility will decrease. So this is for RTA. We're gonna do the same with ITA. Here's our input. So in ITA, you have to specify a little bit more parameters. So I don't specify the Bose. Oh, here I have it here. So the Bose end step here is 50, which means it will solve the linearized DTE iteratively, and it will stop at 50 iteration. And all the rest are the same except for temp here. So in ITA, it will print out the electron phonon scattering matrix first. So in the first run, usually it will take longer, but that result, you can print it out into this temp file, for example, and you can reuse that for later calculation. So to load it, you just need to specify load scatter if phonon equal true here. So the default is false. So let me just comment this one out, and this demonstrates how it looks like. Okay, so I will go to trans ITA trans, and I will run Perturbo again, same way. Yeah, as you see, the code is right now it's computing the electron phonon matrix, and it will bring out the progress just like the EM sigma part. And to save some time, I actually is gonna stop the job here and show you the output I got from the previous run. It will be in reference folder per.out. And you can see all the output file I got from the GitHub repo that we sent. So just do some simple git clone and you have it. And as we see here, it compute the electron phonon matrix and then do the transport equation. All right, so if say you got the temp file from a previous run, you can just copy that file here, and you set in the input file load eq scatter to be true. Okay, where's my second part? I will run again to demonstrate that part. Like this. Yeah, you see, it's much faster because we already have the electron phonon printed out. Okay, the output are the same as RTA. We have con, TDF, and trans ITA, trans coefficient. So now what I'm gonna do is I can compare the two results, the ITA result. So first I retrieve ITA from the current folder. I retrieve the RTA result from the previous folder. Again, I retrieve the temperature via this attribute and the mobility from here. So I will plot the XX component of the mobility of these of gallium arsenide just to compare. So usually we will expect the ITA result be better than the RTA. So here we see there's some discrepancy between the two. The RTA results actually much better with the experimental, while the ITA overestimated by like usually by 40 or 60%. So the reason is what we have been doing for BT so far, we only consider one electron and one phonon scattering processes. We found in one of our paper that the electron and two phonon scattering processes in this material actually very significant. It's almost half of the E phonon, one E, one phonon scattering. So once we include that one electron and two phonon scattering in our calculation, the mobility of ITA will much better with the experimental, which is slightly lower, not slightly, but a lot lower. So the reason that RTA matched very well with the experimental in this case, we think that is because just some error compensation during the calculations. Okay, so so far we've been doing transport with our magnetic field. Now we can do magneto-transport. So first have a look at magneto-transport. The input will most likely be the same. So we just need to set the count mode to be transmart RTA, specify the K grid, specify our energy window, determine if we want to load our scattering phonon, E phonon or not. So I'll comment this out for now. And as we know in magneto-transport, there's the RTA term plus the term from magnetic field that we have to do iteratively compute on that. So that's why we have to specify some Boltzmann end step here. So here I will prepare a different temper file. So it will be reference temper. Look at that. So here we see, just put it this way. Here we see that beside the first line, specify the number of each configuration. We have the extra 3 columns here, and as you may have guessed, this is our magnetic field. So I just increased the Z component of the magnetic field in each configuration while keeping the temperature the same here. So so later we will plot the whole conductivity with respect to the Z component of the magnetic field and see how it goes. We look at the input. So everything's here. So because it's solved iteratively, so it will take some time. And again, I will just keep the job in the middle. Trans RTA. So we run the turbo again. Okay. So it does not detect the. Okay, so right now it's computing electron phonon matrix. We already know how it goes. So I kill it. Let's see. So I forgot to mention, so in the temp file, there will be some HDF5 files. This is our electron phonon matrix. So what I'm going to do now is just copy that file that I got from previous run to this folder. That's R. and we will run the calculation again. I think I forgot to set something. And yeah, I have to set it to true so we can load it. We run it again. So okay, now the calculation is finished, which is like 2 seconds. And now the output file, again, we also have some text file for conductivity, transport distribution function, transport coefficient. Okay, so I'm gonna skip the post process of this RTA Magneto-transport and just go to the Magneto-transport for the ITA run level. Right. So here I have the input, the EPR file, the TET.h5 file. So I also want to reuse the electron phonon matrix. So what I'm gonna do is create a temp file, a temp folder. Go here and I will soft link the result I got from the previous run. Trans here. Okay, so we see here we have the simple link right here. Let's look at the input. So we want to reload the scattering electron phonon matrix. All the parameters are the same as previous calculation. All right, so I'm gonna run that very quick. Choose.ta, run Perturbo. So it does not really compute the electron phonon this time. And just go to the transform, and it takes like 5 seconds. So only the first run will take some time. After that, if you want to change the temperature configuration or change the magnetic field, it will be very fast. All right, so I'll have a look at our post process script. Again, I will load my object from YAML file, retrieve the B field value, and number 2 here stands for the third component, which is the z-axis. So now we want to get the xy components of the conductivity. So if we see here, I get it from the cont values attribute of our object. So I, instead of 0, 0 in the normal transport, I set it to 0, 1, which stands for xy component. And the rest is just use your plotting script. So now I run the Python script. Okay, so again, we see some discrepancy between ITA and RTA. At 0 field, ITA is overestimate compared to the RTA, but we see that the trends are kind of the same. As we increase the field strength, we see that the Hall conductivities will increase. So it's going down because it's the negative sign here. But again, this result is very underconverged, so I don't expect it to match very well with the experimental. So to get a better match, you should increase the number of Q point sampling, for example, or number of K-grid, etc., until you get the desired value, which match the experimental result. Okay, with that, I conclude my tutorial, and I'll be happy to take any questions.